Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Yes, welcome also from my side. It's my pleasure to introduce the speaker of today's webinar. It's Matthias Karlbauer from the University of Tübingen. Many of you will know it's one of the epicenters of AI in very many directions, but in particular also AI for science. And Matthias did his PhD actually on using artificial intelligence for global weather forecasting. He stayed during his PhD also for internships or stipend visits at the University of Washington in US and in the Earth Science Department in Uppsala University in Sweden. So he already has quite some experience. And now he's doing a postdoc actually focusing on more smaller scale. So I'm really excited to see what his views are regarding atmospheric dynamics and how one can address it with AI at these different scales. Looking forward to the talk.
Cool. Thank you so much, Markus, for having me, for introducing me. I'll go forward to share my slides and then let's dive into it right away. So I hope this is all visible. Let me reduce the Zoom window. All right. So yeah, today I'd like to talk about most of the stuff that I did during my PhD, and also that I was dealing with during my PhD about global weather forecasting with artificial neural networks. And I'd like to talk about like how deep learning improves weather forecasts and how it in the same time reduces energy demands, because that's not like the usual way if we talk about deep learning, but in terms of deep learning for weather forecasting, we see that it can be actually a benefit if you use a deep learning energy-wise. A little teaser starting with, I'd like to show you this video where you see basically, let me start this, where we see a geopotential, which is a pressure field kind of 5 kilometers up in the atmosphere that is being visualized here in the center. And then here in the left, we have the prediction of some deep learning weather prediction model that we will look into later. And in the very right, or on the right-hand side, we have the climatology, which is basically an average over the past 30 years on each particular day. So this is very smooth, but it's a reasonable baseline to come up with. It's not trivial to outperform this baseline. Now, what I want to show you on this video is basically that we have this observation unfolding like we started in June or in summer, basically. And this now turns into winter. And an impressive thing is that our model that we see on the left-hand side, it turns into colder temperatures on the Northern Hemisphere if we turn into like towards October, November. And if I fast forward this a little more, we see, well, all the way through December, it's fairly cold on the Northern Hemisphere. And then later, if we go to spring, and so we see that the temperatures turn, well, warmer again on the Northern Hemisphere, just on closed loop prediction of our neural network system. And this is quite impressive that this model basically runs stable for so many time steps. We are talking of thousands of time steps that this model runs autoregressively. And it doesn't collapse, and it still produces reasonable states of the atmosphere. I mean, it certainly does not match the ground truth, but it's much more accurate or much more crisp than climatology, for example. And it's really producing reasonable states. So we will look into this, and we'll also see how other deep learning weather prediction models that are developed by other institutions and also big companies, how they compare. Short credit goes here to Nathaniel Creswell-Clay from the University of Washington, who created this video, thankfully. So another thing that I want to quickly mention is what I just said. Like, I don't go into details here. We look at this graph at a later point still, but we see here the ground truth. This is basically the evolution of the geopotential over an entire year. And what we see is that our model pretty much resembles this ground truth, whereas other models, they really go bad, or like really they turn into exploding activities, or they really don't capture this seasonal trend. But other models are accurate, and we will look into, well, why certain models can do this or can't do this so accurately. With this, I'm introducing you to the agenda that I'm planning to talk about today. Namely, I'd first like to time travel a bit about the evolution of deep learning weather prediction, which I find quite intriguing. It's not that old yet, but it has been a huge improvement in forecasting accuracy in these deep learning weather prediction models. Then we will look into how different deep learning weather prediction models compare, and how they compare against numerical weather prediction, like the traditional way of how forecasts are generated since the past 100 years or so. And we will also inspect how deep learning weather prediction models perform on extreme events, and then later touch on, well, how we should represent data to most accurately present these or generate these forecasts. And we'll also look into runtime and energy consumption of numerical weather versus deep learning weather prediction models. And we will see, this is more towards my postdoc work that I'm currently doing, how basically, I will come up with some explanation why deep learning weather predictions might be improving numerical weather prediction models. And that's going to happen on the example of vertical heat flux. So that's going to come in the next 45 minutes or so. Good. So jumping into the time travel of deep learning weather prediction. The first attempts basically that were really, I'd say, reasonable and on a larger scale were in 2019, when people from University of Uppsala, like July 10th in 2019, when they trained a unit on predicting Z500. Z500, that's just that quantity that we've just seen in the previous video, the pressure field around 5 kilometers up in the atmosphere. And predicting this pressure field over time into the future, like out to, this was out to 2 weeks. We have lead time here on the x-axis. And then the error that is, well, basically accumulating or growing with further lead time, or with increasing lead time. We see that that these two people, like Sebastian Scheer and Gabriele Masori at Uppsala Universitet, they were observing that the coarser they choose the time step. So the further they jump from step to step, like whether they use 1 hour time stepping scheme, or 2 hours, or 3 hours is this, or even like 240 steps in one step, 240 hours in one step. They see that the error kind of decreases, and they came up with this kind of 6 hour time stepping frame or resolution, which appear to be a fair trade-off between granularity. You still get some kind of daily changes in temperatures, etc. But still, you don't your error doesn't grow as fast as if you operate on a 1 hour time stepping scale. So this was kind of the first work that was based purely on Z500. So this model that received geopotential at 500 Z500, and it also predicted that quantity. Now, in pretty much the same year, or very closely, Jonathan Wen and Dale Duran at the University of Washington in Seattle, they posed the question whether machines can learn to predict the weather, and they also they basically accomplished the same task. They trained a unit to predict the Z500 quantity out to it was also 14 days. We only see 3 days here. And they compared it to a numerical model. Like in this case, they compared it to the barotropic model, which basically is defined to predict the Z500 quantity by means of, well, conservation, etc., like a physical model. And when they trained the deep learning models, they found that this deep learning model, which received Z500 as well, like that's the only quantity that this model receives as input, and then predicts that one, produced much smaller errors compared to this numerical barotropic model. And that was quite an intriguing finding, where they said, well, if we use deep learning, it can extract some stuff or some information from the quantity of interest that makes it predict this quantity much better than the numerical model that we would use otherwise. Still to mention is they compared this also to a full numerical weather prediction model, which did not only receive Z500 or process Z500, but a bunch of other variables like Z500 or pressure in different vertical levels, and also air temperatures at several vertical levels. So this full numerical weather prediction model, which has way more parameters to process, it's certainly much better than this deep learning model, which only operates on Z500. Yeah, this is out to 14 days. Then here we don't have the barotropic model here, but yeah, we see that this deep learning model basically does a reasonable job in predicting this quantity of interest. So with this, the cornerstone was set, kind of, but somewhat in the same year, a little early even, the ECMWF, that's the European Center of Medium-Ranged Weather Forecasts, well, published a new dataset, ERA5, with substantially facilitated global data-driven deep learning weather prediction. And that is because, well, ECMWF also had previous products like ERA Interim, but this ERA5 really improved the quality of the dataset by a large margin. And this ERA5 dataset now, it is of high quality and quantity, which we both need for deep learning models, as you probably know. And this ERA5 data, it's really containing hourly data from 1949 out until today. So this is insane. It's on 0.25 degrees resolution, which amounts to about 25 kilometers at the equator. And it contains, well, a huge amount of pressure fields, like vertical pressure fields, and more than 100 surface fields. So it's really a huge data set, counting petabytes of data. And this is a key for global data-driven deep learning weather prediction. And with this data set, the folks from Seattle, they moved forward and not only used Z500 now, but also included three more prognostic fields. But they also transitioned to another way of representing the sphere. And that is, they use this cubed sphere model, which neatly reduces distortions. But we will look a little more into ways of representing data. When they moved to these four prognostic variables, like they had Z500, they had temperature at 2 meters above ground, and they also had 2 more pressure fields, if I'm not mistaken. Using these 4 prognostic fields, they could improve their forecast substantially. And what we see here is basically this blue model is their deep learning weather prediction unit using the cubed sphere data representation. And they could outperform a coarse IFL, like numerical weather prediction. Like this is this orange one. It's a numerical weather prediction model on a very coarse resolution. Yet their model, their deep learning model, was not as accurate as other numerical models on finer resolution. And kind of the holy grail is this ECMWF control, which is the integrated forecasting system. It's the numerical weather prediction model from the ECMWF, and that's kind of the quantity to beat, or the model to beat. It's really the state of the art in numerical weather prediction. And yeah, we see that increasing the number of prognostic variables and also changing the data representation improved the forecast quality substantially. Now seeing this huge Array5 dataset, this attracted like big players like NVIDIA and Google to join the competition and to look what they can do in weather forecasting. And NVIDIA designed a so-called forecast net, which used 20 prognostic variables. Google's GraphCast, it uses 227, so this is an insane number of prognostic fields. Yet it's not as much as the numerical weather prediction model, like the NWP or the ECMWF's numerical weather prediction model. It still uses about 800 prognostic fields. So GraphCast is still like a quarter, like only uses a quarter of their variables. Nevertheless, we see that ForecastNet basically, if we again compare their scores, we see that they reduce the error compared to Wen et al. Like this is the Seattle paper that we've just seen, or basically a follow-up of that. But nevertheless, we see that the ForecastNet improves even further, but it still doesn't reach the holy grail. Like ECMWF is still superior and produces a smaller error over the entire lead time range. However, when GraphCast published their results, it looked like we were there, and Google actually made it. Like GraphCast was really outperforming ECMWF here. So what we see here in black is the evolution of the error from the numerical weather prediction model, and in blue we see GraphCast, which produces smaller errors over the entire lead time range. So this is impressive, seeing that GraphCast can produce smaller errors despite using just a quarter of the prognostic fields compared to the numerical weather prediction model. Roughly at the same time, there were a couple of transformers, or basically also around, well, this was November 2022. That's when Huawei published their Pangu weather on arXiv. It's now a Nature paper, and they also showed that they basically outperform numerical weather prediction. And they were also impressively accurate at predicting the track of hurricanes. So what we see here is in black, actually the true trajectory of the hurricane. And then in red, we see what Pangu weather predicted, where the hurricane would travel basically. And in blue, we see what the operational numerical weather prediction model predicted. And it seemed like this Pangu weather was fairly accurate at predicting these hurricane tracks. Very recently, there's also Microsoft who published their Aurora model, which is now a foundation model. It's really designed to accomplish a wide variety of tasks. And we see that this Aurora model, at least according to their analysis, is even outperforming GraphCast. It's also outperforming Pangu weather. And we know that since GraphCast has already outperformed the numerical weather prediction model, we see that Aurora kind of must be the state of the art model at the moment. State of the art deep learning weather prediction model, certainly. Now looking at ECMWF, basically the people who are doing the numerical weather predictions, who are really expert at this, they are also shifting gears and well, building their own artificial neural network. So they call this the AI forecasting system. And they also see that their model improves the, like here in blue is the AI system, and then in red we have the numerical weather prediction model. And they really see that the deep learning model is definitely outperforming the numerical model. So this is now also officially kind of published by ECMWF themselves, that deep learning has quite some potential at improving weather forecasts. What I like very much and what I found quite intriguing about the AIFS is that they are working on this N320 reduced Gaussian grid, meaning they're really taking care of how to represent their data in order to facilitate the model and concentrating really on the forecast task. And I will talk about this a little more on the next slides, and well, make this point more well, kind of more clearer basically. And I want to show how basically the equirectangular representation, like the way how the Earth is often represented in this rectangular way, that this imposes huge distortions at the polar regions. Probably everyone's aware of those, like looking at the here at the south, at the Antarctica, we see that it looks like Antarctica would occupy huge amounts of space, although basically looking here left, when it's on the sphere, it's basically just a very small, it's not small, but it's not as huge as it might look at this equirectangular projection. And well, what we see, if there's some kind of nice rule of thumb that I once heard, like on a well accurate projection, Greenland should fit basically 7 times into South America. And if we look at this projection, like this equirectangular projection, and we look at Greenland and at South America, we see that Greenland really doesn't fit 7 times into South America. Whereas Greenland here, well, it would fit like 7 times if it was like on the sphere. Now there's another neat data representation, which is called heel-pix. Details are on the next slide. This heel-pix projection resolves like these distortions around the polar regions, and it neatly makes sure, like if we look at this projection and we look at Greenland and see whether it fits like about 7 times into South America, we say, well, this might work out, and this means that we have way less distortions in this heel-pix representation compared to the equirectangular presentation. Little more details about this heel-pix projection, which I really like a lot. I worked on this when I was visiting the folks in Seattle, University of Washington. We implemented this heel-pix projection in the model that they are using and that they were using. The heel-pix projection is mostly used in astronomy, and we were now the first to apply this to metrology. And this, well, heel-pix means basically hierarchical equal error isolatitude pixelization. And a neat thing of this projection is that we basically have the sphere separated into 12 main phases. We have 4 phases on the northern hemisphere, equally 4 phases on the southern hemisphere, and then we have 4 phases around the equator. And a neat property of this projection is that we can arbitrarily subdivide these phases. Now we can say, well, we won't have like each phase subdivided by or represented by 4 patches. And so each phase now constitutes of 4 sub-patches. And we can make this like arbitrarily fine. Another property is that all these patches, irrespective of how much we subdivide them, they are of equal area, which is a super valuable property if we want to apply convolutions or something like this. And the patches are distributed isolatitudinal, meaning they are aligned along constant lines of latitude. So they're really properly lined up along one constant line here. And here's a neat visualization of how, well, dynamics would look like if we simulate them on these three different projections. Like we have the equirectangular here on the very left-hand side. Let me jump to the beginning, and we see that it looks like we have huge, well, speeds, or the quantity is propagating very far and very fast in the northern and southern poles. Whereas if we look at the other projections, we see that it is basically only traveling fairly slow. However, we see, well, this is basically amplifying how big the distortions are in this equirectangular projection. And by looking at this, we just see how much models will have to compensate if we train them on this equirectangular presentation. Like they will have to compensate that information travels actually not as fast as it appears on the rectangular representation. However, if we transit to this cubed sphere or even to this heel pix, the model doesn't have to compensate for these different speeds that are caused by the projection. So here I'm pointing out like the effect of the data representation, and I'm only aiming to focus at these two curves, namely that green dotted line here at the very top, which is the UNet from Seattle on the cubed sphere. And if we switch to using the heel pix projection, we see that the error decreases substantially. Like only by switching the way we represent the data, we already reduce the error substantially. I don't have a plot of the rectangular representation here, but it would be way further up here. So really choosing a wise or an accurate representation of the data really helps to reduce the error, because your model can really focus on the relevant stuff. It doesn't have to compensate for distortions or so. And another really neat property of using such kind of reasonable projections is that your model turns much more stable. Like if we use this heel pix projection, we can really unroll a forecast out to 365 days without going into these like bad activity regimes. And I'm pointing this out because there's this recent spherical Fourier operators from NVIDIA as well, which is also defined on the sphere, and therefore is also running very stable. Like their previous paper, ForecastNet, it was operating on this equirectangular grid, and it wasn't stable out to, I think it might have even blown up to 2 weeks or so. And when they transitioned to spherical Fourier operators, they really went into this stable regime and well had the model generating stable rollouts out to 365 days, which the other models like GraphCast or PangueWeather, they really don't show this behavior as neatly. So having seen all these different deep learning weather prediction models, I'd like to point to some intercomparison projects. And first, I would like to point out WeatherBench 2, which compares the original architectures. It looks at the original PangueWeather implementation, for example, GraphCast implementation, and then it compares these full-blown models against each other. And they're using these scorecards, which is a way of representing the performance. And as a baseline, they choose the numerical IFS model here, which is the state-of-the-art numerical weather prediction model. And whenever a scorecard, like a patch, appears to be blue, then the model is superior compared to that baseline model. So looking at this, we see that GraphCast is more accurate than the IFS at predicting 2 meters temperature at a lead time of 1 day, for example. And this is slightly different for Pangu weather. So Pangu weather didn't seem to be more, like it seemed to be slightly worse than the IFS, at least in this analysis. So this is a nice intercomparison study. There's a lot of other models involved here. It's just a small fraction that I'm displaying here. This is provided by Google, and now a drawback of this kind of weather bench 2 study, or it's not a drawback, but one thing that was questioned me quite a bit was seeing that these different architectures, like Pangu weather is a transformer, GraphCast is a graph neural network, then we had ForecastNet, which is based on Fourier neural operators, we have UNets, we have all kinds of different architectures. And now it's really hard to understand which of these base architectures is now most suitable for deep learning weather prediction. And that's why I kind of designed, or we designed this DLWP bench during my stay at Amazon. And our aim was to really compare and contrast the backbones of these deep learning weather prediction models, as well as the deep learning weather prediction models themselves. We wanted to retrain those models under controlled conditions, controlling for the number of variables, the training protocol, the evaluation pipeline, all these things we really wanted to keep controlled, to understand which of these models is now actually better. Is it like I wanted to know whether GraphCast is superior because is it a matter of the architecture, or is it a matter of using more prognostic variables or of the training protocol or so? And here we found that was quite interesting actually, that conv-LSTM, which is a fairly old architecture, it's super accurate if we look at short lead times, like out to 5 days or so. Conv-LSTM is superior to other architectures. But we also looked at the memory consumption and the runtime of these different models. It was quite impressive to see how different models scale in terms of memory and runtime, and how they compare in terms of predicting the atmospheric states out to 14 days into the future. Having seen that deep learning weather prediction now is basically superior to numerical weather prediction, I was always wondering whether deep learning weather prediction is also working properly if we are transitioning into warmer climates, to be expected in the future, and how deep learning weather prediction models perform on extreme events. Because deep learning in general is said to be fairly bad at generalization. So, and also in terms of rare events, like for example, extreme events that are occurring there rarely, we might expect that deep learning is fairly poor at predicting those. However, first looking at how deep learning weather prediction performs on warmer climates, we see a study of the ECMWF that these models, when operating on a warmer climate generated by a climate model in 2049, for example, these models all generate reasonable forecasts still. So it didn't seem like the models really turned bad once we had higher air temperatures or something like this. And these numerical weather predictions were still reliably predicting the atmosphere out to 14 days or so reasonably well, even though the climate shifted by, 1.5 degrees or so. So this was a great observation, basically, telling that numerical weather, a deep learning weather prediction is still reliable even in changing climates. Another point they found was basically that these models all had some biases or some drifts, except for GraphCast, which seemed to be fairly stable. But I'm really only touching this very briefly. Interestingly, and the main argument is that deep learning weather prediction models are stable even under changing climates. Now, ongoing work that we are currently having here with the student, Andreas Scheible, he's looking at how these deep learning weather prediction models now perform on extreme events. And we are interested in, well, can these deep learning weather predictions now predict extreme events that are rarely represented in the data? And what we see here is on the x-axis, the time of days until the cold spell event in this case. Like we see how these models, like the growth of the error in terms of when predicting a cold spell event, a particular cold event in North America. And what we find is basically Tigge, that's this black line. It's hard to see, unfortunately, but Tigge is the numerical weather prediction model. Then we have ForecastNet, it's up here. And then we have GraphCast, PanguWeather, and Aurora. And these are all below Tigge. So we see that these models are producing smaller errors than the numerical weather prediction models. And then, well, this is now a plot relative to Tigge. Like in the center, we have the numerical weather prediction model. And if the error of the, like if a curve now lies below 0, the model produces a smaller error. If it's above 0, the model produces a larger error. And we see that basically Aurora, GraphCast, PanguWeather, they all reasonably well predict this. Well, this is statistics over many extreme events. And maybe GraphCast is not really well capturing this as it looks like here, and PanguWeather neither. But still, Aurora is reasonably well, it's staying below Tigge. And this kind of shows that even under extreme events, which are rarely represented in the data, these deep learning weather prediction models can generate accurate forecasts. And that's a neat insight, I'd say. And this insight is basically supported by other studies recently published at the University of Uppsala, looking at these scorecards. Interestingly, GraphCast here, it's more accurate if we look at cold, like at the 5% of cold extremes. However, if we look at the extremist extreme events, like only the top 1 extreme events, then it appears like GraphCast and PanguWeather turn worse than the numerical weather prediction model. So there's quite some research still going on whether the very extremist extreme events are captured well or not. Now, one thing that drives me quite a bit is looking at the energy demands of numerical versus deep learning weather prediction. And this credit now goes to NVIDIA's ForecastNet paper. They are really doing a nice evaluation of energy and runtime comparison. And one thing that I want to focus on is basically this column, and that's the ratio between the numerical weather prediction and the ForecastNet. And we see technically that the ForecastNet, it takes about 12,000 times less energy than the numerical weather prediction model. And this is impressive. Like really, like this deep learning model takes 12,000 times less energy to generate a forecast when comparing it to this numerical weather prediction model. And that's quite an intriguing insight, because these numerical weather prediction models, they are impressively expensive. They need to solve their equations in each grid cell, and there's tons of grid cells in their model, like the discretization of the sphere. And thus, you need really supercomputers to run a numerical weather prediction model. And this gives rise to deep learning weather prediction models consuming less energy compared to numerical weather prediction models when generating forecasts. Other impressive statistics were like just training the ForecastNet, which is usually called to be the very expensive part of when dealing with deep learning. Training ForecastNet requires as much energy as generating just a single 10-day forecast with a 50 ensemble numerical weather prediction model. So training the entire model just takes the same energy as just generating a single forecast with the IFS model. So this is super impressive as well, I think. And then looking at runtime, ForecastNet takes 7 seconds about to create a 100-member 24-hour forecast on a single node, which is 45,000 times faster compared to numerical weather prediction. So summing up, it's impressive to see how numerical weather prediction or how deep learning weather prediction can be much cheaper and also much faster than numerical weather prediction. And looking at Microsoft's Aurora, they are reporting that they are about 5,000 times faster. And they are also more accurate than numerical weather prediction. So in terms of runtime and accuracy and energy consumption, there's a lot gain with deep learning weather prediction. And that's I like this quite a bit because that's not a common argument for deep learning. Now looking at the question, how can deep learning weather prediction actually be superior to numerical weather prediction? Like we have seen these plots from GraphCast, and we see that deep learning weather prediction outperforms numerical weather prediction. But how can that be? And there's 2 points that I'm hypothesizing or that I'm reporting here. That's first, with deep learning, we have this data-driven model which can just capture and learn like any fine nuances in the data that the numerical weather prediction model might miss. Like the way how the physics is represented in the numerical weather prediction model, it might be slightly inaccurate or it might be approximative. And the data-driven model just can really nudge on this and capture all these fine nuances that are necessary to unroll the evolution of the atmosphere reasonably well. Another point is subgrid parameterizations in numerical weather prediction. And there's basically processes that are unfolding on scales that are smaller than the model resolution. These are parameterized in numerical weather prediction, and these parameterizations, they are fairly approximative, and therefore that's also a playground where deep learning can excel and really learn kind of approximation more accurately from data. And I want to give one example, and that is basically looking at sensible and latent heat flux. Sensible and latent heat flux are basically vertical energy transport from the planet's surface into the atmosphere, and then tells how the atmosphere basically evolves. And I'll try to be a little quicker here. Energy can basically be represented in terms of sensible or in latent energy. And sensible energy is the one that we perceive, like basically the temperature of a glass of water, basically. If you increase the temperature of the water from 15 to 100 degrees, we have increased the sensible heat, the sensible energy in that medium. Now, once we are at 100 degrees and we add more energy to that system, then we basically see latent heat increasing. And that is basically a phase transition, like where water turns into vapor. And then we have more energy in that medium, but still the same temperature. And that's nicely visualized on this plot here. Basically, we have some quantity, and we add energy to that quantity, and over time the sensible energy in that, or the sensible heat in that system, increases. Now, at a certain point where the phase change occurs, the sensible heat does not increase further, even though we add more energy to that system. And we see that the latent heat increases, and that's basically the phase transition. And once the entire medium is changed into the next phase, and we see that the sensible heat again keeps or continues to increase. Now, the sensible and latent heat fluxes, these are crucial or substantial for atmospheric dynamics. And that is why, or that's basically seen here, where we see that basically looking at the energy coming into our system, our Earth, we see that the sun might propagate like 100 units of energy, and then we see that there's only 7 units of that 100 units that is being transformed into sensible heat flux into the atmosphere, whereas 23 units of energy are transformed into latent energy. So there's lots of latent energy that propagates from the atmosphere, from the surface into the atmosphere. That's what I just said. And there's a traditional theory, which is called Monin-Obukhov similarity theory. It'll be rather quick. And this appears to be kind of like, this tries to approximate sensible heat and latent heat and tries to tell each numerical weather prediction model how much sensible and latent heat enters from the surface, like the planet surface, into the atmosphere. Now, what we did recently with people from the University of Hohenheim was we looked into how accurate Monin-Obukhov similarity actually is. And we found that here on the x-axis, we have the prediction of the model, like in this case, the Monin-Obukhov prediction. And on the y-axis, we have the observation. So ideally, the prediction or the model should lie on the main diagonal here. But we see that the Monin-Obukhov similarity theory, it deviates quite a bit from the main diagonal. However, if we predict the sensible heat flux using a multi-layer perceptron, we have a much more accurate fit, and we really hit the main diagonal. And we did some feature importance analysis and found, well, our model looks at the same variables that like the traditional Monin-Obukhov theory. So this kind of aligns. However, we might gain something if we add other variables, for example. So this is the case for sensible heat. Now, looking at latent heat, the story looks much differently, way different. And that is, we see that the Monin-Obukhov similarity theory is much more inaccurate. And still, our machine learning multi-layer perceptron is accurately hitting the diagonal. And interestingly, what I found here now is that the traditional, like this Monin-Obukhov similarity theory, it was using different variables compared to what our model found important to predicting latent heat flux. I'm trying to wrapping up here now in just a minute or so. And we found that, well, if we increase, if we provide radiation into that model, we apparently can improve the prediction substantially. And there's kind of this land atmosphere feedback initiative, which is now looking at these processes very dedicatedly. Well, it's a huge consortium of experts all over Germany, and that's now really dealing about, well, how do these land atmosphere feedback processes evolve, and how does vegetation influence it? How does basically the heterogeneity of the surface affect all this? And that's crucial for numerical weather prediction models in order to generate their forecasts. So there's some follow-up that we did, but I will skip over that and come to our conclusion. And that is that deep learning weather prediction is competitive or produces even better forecasts compared to numerical. Deep learning is outperforming numerical weather prediction nowadays. But still, deep learning depends on the high quality data that is generated by numerical weather prediction. As I mentioned, like this ERA5 dataset, for example, it's coming from a numerical weather prediction model. So all this is built on numerical weather prediction models, basically. So really should credit the effort that people spend into developing numerical models. It's crucial to represent the sphere adequately for deep learning weather prediction models. Then we found that, or we've seen that deep learning can handle extreme events and work with high energy conditions that are expected to occur in the future. And we have huge potential when incorporating more variables and satellite observations. So there's quite some accuracy to gain if we increase the amount of data. Then we found that latent and sensible heat flux are poorly understood physically, and that we can improve this with machine learning. And ultimately, this will again improve numerical weather prediction models, and maybe we can generate more accurate data sets then to train deep learning again. So this is all kind of a circle, and all should go kind of hand in hand. Yeah, that's it. I'm still sending acknowledgements to lots of people. I'm grateful for their support. And with this, I'm at the end and want to thank you for your attention.
Yeah, thanks a lot, Matthias. That was certainly a very great overview and right through actually also the developments that have been, I mean, where like 5 years of development looks like a much longer time span because this field is developing so rapidly. So very nice overview, and I guess your second part deserves maybe another seminar even, the one on the land atmosphere interactions and latent and sensible heat fluxes. But let's see, we have time for a couple of questions. Yeah, there was one. It's not very specific, but somebody, namely James Reed, was interested in what tools actually do you use. So possibly a more technical question.
Concerning tools, yeah, maybe I can. Yeah, thanks first of all, Marcus, for. I also had the impression that I could devote another presentation for this sensible heat flux, etc. stuff. Nevertheless, the tools that I'm using is basically I was mostly working with UNets, so just these U-shaped deep learning models, which seem to be fairly accurate already. And maybe can jump to that particular slide. I think it was here, like where we compare different deep learning weather prediction models. That's here. So here in dark green, we see.
We don't see the slideshare still.
Can I start the screen share? Okay, let's see. So do you see that?
Yes.
Okay, cool. So here in dark green, we do see the unit, which is kind of comparable to other methods if we increase the amount of variables. And I always use units because they are fairly kind of they're easy to handle, they are kind of easy to implement, and they are easy to optimize. I also found when I did this intercomparison study that Swin transformer, which is the basis for Pangu weather, for example, but also for other, like also for Aurora and also AIFS, like ECMWF's forecasting, deep learning forecasting system. The Swin transformer is also fairly accurate, and it's also nice to handle. Like there's not so much of hyperparameter tweaking involved. And in particular, if we compare this to graph neural networks, like this mesh GraphNet, for example, that's this purple curve. It was really hard to get this optimized. And similarly, this graph neural network, like GraphCast itself, I had quite some severe difficulties getting this trained properly. And this was different when using UNet or Swin transformer. Maybe so much for the tools. I'll stop my sharing here again.
Yeah, I can't read the mind of the person that asked, but maybe the question was also really about the environment. So I guess, I mean, mostly it's PyTorch.
Okay,
I
I
guess.
see. Yeah, right. So I was only working PyTorch for these projects. I mean, TensorFlow, PyTorch, they probably don't differ so much. Yeah, I was definitely using on PyTorch. And maybe also the compute that I've used. I didn't have like this massive amounts of compute available, like how GraphCast required, for example. I was mainly working on 4 A100 GPUs when doing this stuff in Seattle. So this is 4 times 80 gigabytes, which is quite big already. And then also when doing this intercomparison study at Amazon, I was basically using I think it was just single GPUs single GPUs with 20 gigabytes or so. I really try to keep this on small scale.
Good. Yes, thanks. So there's another question, or actually two now in the chat. One is from Tessina Grant Moloney. How would you describe the appropriateness of using something like this to predict or manage wildfires, given that wildfires are dependent on some weather variables such as humidity and drought conditions?
Yeah, good point. I remember some kind of project, Marcus. I think you posted this fairly. That was 5 years ago or so. Like how wildfires might propagate through space. I'd say deep learning has huge potential in doing this. It's probably hard to get the point where the fire will ignite, where it will start off. But you can definitely model probabilities and capture the droughts and like seasonalities and these kind of things. And you certainly can represent the likelihood that wildfires might ignite or just break out. So machine learning definitely has huge potential here, and I'm pretty sure that it's also being used nowadays.
Yes, and then next question from Zaharia Thurston. The question is if you can re-explain how deep learning weather prediction is less energy intensive, because there was the assumption that deep learning frameworks are very energy intensive, as you also said, for developing AI products. And I had a question related to this too, and I think it relates. So, Betty, if you do the comparison between NWP, classical, and the deep learning one, I think one is also changing the hardware architecture, Betty, from CPUs to GPUs. So, what is actually the effect of this? Would be actually my question. If you can comment on that.
Yeah,
but maybe you first re-explain it.
Yeah, that's like great point. I'm happy to expand on this because I'm very intrigued by this. I like this very much. Yeah, first of all, the way numerical weather prediction works is you have the sphere, then you discretize the sphere into small patches. Like you have hundreds of thousands of patches that cover the sphere, and then you go into vertical, like you go into the atmosphere, you go up into the air, and so you have like hundreds of thousands of grid cells. And in each of these grid cells, you are solving with numerical weather prediction models, you are solving a set of several equations like mass conservation, Navier-Stokes equation, all these kinds of things. And you have to do this in every grid point, and this just imposes huge amounts of computation. Like you really need to solve hundreds of thousands of equations in each for each model step, basically. And this is just super expensive. Like you need supercomputers with huge loads of CPUs to basically just compute all these equations. Now with deep learning, you can, first of all, you can use much coarser step sizes. You can step like every 6 hours or so, which you can't do with numerical weather prediction if you want to operate on very fine scales. And basically you can solve this, or you train your model, and once this model is trained, it's just really a forward pass through our model. It's just a couple of weights. It's no equations that need to be solved or something like this that is involved. It's really just a forward pass, and that's super quick and energy comparably cheap energy-wise. So that's why numerical weather prediction is so much cheaper. And the point that you just mentioned, Marcus, transitioning numerical weather prediction, or the difference is the hardware indeed. Like for numerical weather prediction models, we need these CPU clusters with, all these hundreds of thousands of CPUs to solve your equations. If we operate with deep learning, we have GPUs, like graphics processing units, and this is just much more efficient and therefore much cheaper than in the end as well.
Yes, I mean, I have to say that I think the numerical people also try to transition to GPUs, so to refactor their code into GPUs. I know it for climate modeling. So,
It's also
the question is what, but I don't think it's a factor of 1,000 that will just come through that. I mean, this is clear.
I can't really comment this, but I think it's likely that you can gain quite a bit. I only know that numerical models are really written in this very old Fortran code that's kind of no one really able to really dig through this or go through this anymore. Really transitioning to modern GPU would probably also save lots of time and energy already.
Okay, we have more or less come to an end, I understand, but there is one more question. Maybe I have one. Let's see how fast we can be. So one by Alessandro Grassi, commenting first of all for the interesting talk, but then the question was a bit if there's more explainable AI or if you have experience more on explainable AI with respect to those models and feature importance.
Well, I haven't seen so much of explainable AI in global weather forecasting, but if we really go down to the fine scale processes, like about this sensible and latent heat flux diagnosis, there's quite some work in this, and we've also like touched on this, like looking at how much the model relies on certain input features. I mean, you could do this with global weather forecasting, like deep learning weather prediction models as well. But I'm not aware of any study that did this. I mean, it's likely that something like this has been done, but I'm not aware of so much there. But it would be interesting to understand which are the key driving variables that basically are, well, crucial to generate an accurate forecast. But then it's probably difficult because you have so many like all these prognostic variables. It's probably depending on the target variable that you are predicting which of the input variables are more important. And so it's very much, it's pretty intertwined there and probably heavy or difficult, more difficult to get direct dependencies from one input variable to certain target variables.
Yeah, thanks. I may have one comment that you might want to respond to also. So it's a little bit, you were, to my mind, relatively optimistic on the distribution shift or generalization capabilities with respect to climate change. You showed this example with 2049,
Right.
yeah, 49 prediction kind of, or predicting the weather under these new states. Well, I mean, but the thing is that then the climate is not really too different. And I mean to remember that people also did experiments regarding these subgrid parameterizations. Again, it's more in the climate modeling domain where +2 degree or +4 degree actually then the thing failed. They also found remedies for that, but I think it's still quite an issue that one cannot just assume that distribution shift is easy, you know?
Yeah, a good point. I mean, I still remember kind of these works, Tom Böckler also, and Stefan, they did something in this respect. Definitely, I would agree that, I mean, what I've showed is these were kind of 14 days forecasts, I think, on a different climate. And I might imagine that if you run these models longer, that they still kind of propagate back to the training dynamics where they have been trained on. So you can't, I wouldn't expect these models to really be stable in climate perspectives. Like I wouldn't expect this model to still continue predicting on this higher atmospheric energy state or even increasing it further. That's something I wouldn't expect from deep learning weather prediction models.
Okay, yes, thanks again for this really, really nice overview talk. It will be also is recorded and will be is available to the community, which is very nice. So maybe you will also get feedback from the community by email and so on. So it's nice to have you in this webinar, and I'm looking also forward to the next one, which I think is in 2 weeks. So thanks again, Matthias.
Thanks for having me, and happy to connect.
Yes.
See you around.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.